Thank you. So let me dispel the misconception. I don't actually understand machine learning that much. But we have a lot of information and stuff to go through. So for instance, if you're curious about this strange title, I'm afraid that's gonna wait after the talk. I'm happy to do that, but we have a lot of information to go through. So first thing, this whole talk is a Jupyter notebook as appropriate in a PyCon conference. So you can download it from my repo, either here or possibly later to try the code. So in this presentation, there are no equations, there are no formulas, no strange mathematics, but there's a lot of Python code, and that's on purpose. Because for me, to understand something, I need to put my hands on it. And coding that is the best way how to do that. So a very short introduction. I'm a software developer for maybe almost 20 years. I spent a lot of time in the Ruby and Rails communities. I spent a lot of time evangelizing about Git and NoSQL, etc. At some point, early in the life of the company, Elastic, I joined them, and I was responsible for the official clients in Ruby and then in Go. And also, search is something which is really close to my heart. I spent almost a year at Cisco Digital, the NGO here in Czech Republic, helping them with strategic decisions and some technological aspects. Despite being, a professional developer for a long time, I'm actually a philosophy major. I studied philosophy. My thesis is on Adorno. I spent most of my studies in one way or another focusing on language and philosophy of language, and that kind of, I think, shows in this talk. All the information is on my website, including email. Don't hesitate to write me. I do respond. So when we mention machine learning, deep learning, or artificial intelligence, and when you try to kind of understand what it's all about, this is what you get. Like the vanishing gradient problem in RNNs is often mitigated by something called long-term short memory. I don't know about you, but for me, this was really hard to understand. So if your reaction is this, then it's completely natural, at least to me. So I ignored artificial intelligence, machine learning throughout all my life, basically, because of that, And then this seismic shift happened when OpenAI released ChatGPT last November, so almost a year, or not even a year ago, right? And that triggered something like a Cambrian explosion of interest in, machine learning in a very broad sense. I guess for me, for you, for everybody, even for common people, suddenly, it's a normal topic you can talk in a pub. So I thought, I can't no longer ignore this topic. This is too important, and it's gonna, in one way or another, I think, dominate our field. Because many problems in IT actually will or can be reframed as AI problems or machine learning problems. And that's what I think. Because let's have a very trivial example. I give you a bunch of text, like unstructured text, and I tell you, extract all the email addresses from the text. Your first thought is regex, right? Now, as the joke goes, now we have two problems, right? But that's not the worst thing, A properly trained machine learning workflow can do much more than that, It's not like single purpose. It can extract email addresses, but also names and other named entities like locations or financial data. So it is my understanding that we are kind of on a crossroads right now, and we will see machine learning and artificial intelligence dominate, basically, our field. So what is our itinerary in this talk? We will have a look at what are text embeddings, because that's, to me, and was to me, a crucial concept to understand how the large language models works, how similarity search works, etc. We'll have a look at a very specific use case, which is semantic search, but there are many others. All recommendation systems and sentiment analysis is also based on that. And we'll have a look at embeddings for other media, because we can feed the models something else, not just text. Like could be images, could be video, etc. So let's dive right in. What are text embeddings? Text embeddings on the surface is a basic mechanism for every natural language processing, be it LLMs, be it machine translation, sentiment analysis, recommendation systems. And to have a formal definition, we could say that they are numerical representations of text. So that text could be a single word, but a couple of words, like a phrase, a sentence, paragraphs, larger type of content. No matter what, text embeddings represent this piece of text. And when you look at them as a layman, it's just a long list of numbers. And we will see that on the next slide, but there's nothing really esoteric about them. It's a long list of numbers. But we can see them as something slightly different, and that's, for instance, a GPS coordinate for meaning. Because if you think about GPS coordinate, it's a list of numbers. It's just two numbers, latitude and longitude. But still, it's a list of numbers. So text embeddings are that, just much larger. So I promise that we will do everything hands-on, and you can run the notebook, which is the basis for this talk. And what we're going to do, we're going to generate text embeddings using a pre-trained model. This is a very small model from the package sentence transformers, which you can just install, import, and then initialize. That's it. The Hugging Face card for the model has a lot of information about the content it's been trained on. It's a bunch of Reddit, Wikipedia, Stack Overflow, basically as every other model. It's just much smaller than, for instance, GPT-3. So let's create embeddings for just two very simple words, cat and dog. I promised it's just a long list of numbers. Obviously, we display just the first 5, would overwhelm the display. And when I say a long list, the natural question is how long, right? So if we print the length of the list, it's 384. And now, surprisingly, we can query the model, hey, give me the sentence, give me the embedding dimension, as the same number. And this was something which was kind of confusing me. Like, what is this dimension? Why one model has 256, another has 384. Some models like GPT-4 have thousands of dimensions. So we can think of these dimensions, each of these numbers in the list, as different aspects of the phrase or word or sentence meaning, usage, or context. It's not just meaning in a very, let's say, trivial sense. It could be also something like emotional tone. Is this word, and let's keep talking about words because that's what we're doing, is it a positive, negative, neutral word? What is the usage pattern? Is this word common or rare? And in which genre? Because one word could be really common in a specific genre. And what is the social setting for this phrase or word? Is it a formal phrase, informal phrase? And that is the primary way how a pre-trained model understands meaning. Now, obviously, there is a lot of math involved, very complicated workflows to train the model, actually. But on the surface, when you use it like this, it's not very complicated. So, for the rest of the talk, we're going to use pandas data frames a lot because they are really beneficial. We can really easily, display the content, and also we can do a lot of transformations and manipulations with the data, and we will do a lot of these operations. So nothing terribly complicated. Let's create a new data frame. Let's stick the embeddings for cat and dog there. We have one column, two indices. Now, we will need to transform the data to kind of visualize these numbers. So this is not terribly interesting, but we will use the explode method of the data frame and kind of do some renaming and transformation. What we will end up, if we feed this to a pretty basic heat map, is this. And now, I would assume, maybe I'm wrong, but I would assume that this is slightly more understandable for humans than a list of 384 numbers. Unless you're some mathematical weirdo, you can't really understand such a long list. And it's a small list when we talk about machine learning models. So on this heat map, we kind of see some patterns. So for instance, we see that here, the embeddings kind of share something in this specific dimension. They kind of share some patterns in this dimension. But here comes the problem. It's still for us as people completely confusing to get some meaning out of this. We can have some intuition, we can talk about it, but that's it, you know. So what we need to do usually is to reduce the dimensions. And since we're working with numbers, we can actually do that. And here, you know, comes the interesting part. Because we can import an algorithm, this PCA algorithm, principal component analysis, and we can reduce the long array into just 2 numbers. And what we can do now, we can make a function for a scatter plot and place these 2 words on a scatter plot. So there are, I would say, 2 insights here. It's pretty hard to visualize anything which has more than 3 dimensions. Like 3 dimensions we can still work with, maybe 4, including time, it's a video. But then, you know, after that, like there's no way to imagine the thing. For an algorithm, it's not a problem. The dimensions are just some kind of, you know, mathematical aspect of the data. And so we can reduce that long list of numbers into just 2 and plot them. And the second insight is, okay, it's just like 2 circles on a plane. What's interesting about it? Maybe intuitively we would think that the cat and dog would be closer to each other because, you know, both are domestic animals, right? And they share a lot of traits, mammals, furry animals, 4 legs, blah, blah. But if you think about it, we are working in a system which has just 2 words. And now, within a larger system of human understanding, cats and dogs are kind of, you know, close concepts. But if we take them apart and just think about them in isolation, they might, you know, have more differences than something common. So what we're going to do is we will put more words into the data frame. And now comes something you probably, you know, heard before. More data beats better algorithms. That's an old adage in machine learning and in IT in general, you know. Frequently, I encourage you when you will play with something like this or something else, and it doesn't work as you would expect, just use more data. Because, you know, our intuition, human intuition, kind of gets into there, and cats and dogs are similar, but not if you isolate them. So let's use cat, dog, pizza, coffee, asymptomatic. Let's generate the embeddings with a model 1 encode line, and let's do the scatter plot again. Something magical happens right now. So cat and dog are close to each other, coffee and pizza as well. And this really strange, rare word, asymptomatic, is somewhere over there, completely out of the line. Now, what magic just happens? You know, this sometimes leads people to think that there is some kind of black magic when it comes to artificial intelligence, and you can't understand it, etc., etc. I think that a good way how to understand what's happening here is to actually completely ignore the computing part, the mathematical part, you know, the historical part, and let's focus on the language and the theory of language. And this was a pretty, you know, intense insight for me, because when I was researching this whole topic, I kind of remembered language is a system that, you know, that's the thesis of a course in general linguistics by Saussure, and it goes more than 100 years ago. You know. And when you think about language as a system of signs, and this signs represents concepts, not things, and when you kind of go along with Saussure and you think that the sign is actually arbitrary or unmotivated, how Saussure says, you know, now it clicks. Because think about it. The cat represents a furry domestic animal, it meows, etc. And a bat represents the flying mouse, right? That's the normal system of language we have in English. There's nothing, telling us that it couldn't be vice versa. So bat would be the furry domestic animal which meows, and cat would be the flying mouse. The only thing needed is that we share this understanding and we share the same system. I just can't, make this decision on my own, because then you wouldn't understand me and I wouldn't understand you. So this, for ages, is a principal intuition how language works. The nature of the sign is arbitrary in a sense that it's not motivated by anything, and the meaning is is given by the position in the system of language. And actually, that's a pretty good visualization, this scatter plot, of that thesis. And so what Saussure says, what is natural to us as humans is not the language or oral speech itself, with the phonemes and graphemes, etc., but is the ability, the faculty of constructing such a system. And systems like that, we can construct more of these systems. So I think that kind of, is a good baseline understanding why it works, not how. The how is really about training models, mathematics, all these things, but it doesn't tell you why it works. And we can kind of work a little bit with this assumption, returning back to Python, and we can put a word in a different language in that data frame. Let's use word kočka, which means cat in Czech. Nothing terribly interesting here again. We just encode, all the embeddings. Here they are, and let's display the scatter plot again. Okay, kočka is somewhere out there with asymptomatic. Why, right? Like, again, as humans, we would understand if you speak Czech, or at least a little bit, and you know that kočka is cat, you would think that they would be close to each other. But the model has been obviously trained only on English text. So kočka maybe appears there once, twice in some Wikipedia page, but that's about it. It doesn't have any position in the system. That particular word is a complete outlier, almost like asymptomatic. So what we can do, we can actually try with a different model. Almost the same as the mini-LM family, but this one is called paraphrase multilingual. And it has been trained on data for more than 50 languages, where a sentence corresponds to sentences in other languages. When we do all these operations again, we generate embeddings for these words, and we plot it, suddenly cat and kočka are almost on top of each other. Now, the rest of the dots are kind of all over the place. Again, that sometimes happens when you have some limited set of data. Again, same story. It's counterintuitive, but try it and possibly it will work. So that's interesting. Let's do something else. And now we are getting more into the implementation or the use cases for embeddings, because so far it's just charts. What we can do is that we can compute similarity, and specifically cosine similarity, for a query, and our query is cat, and the rest of the words. It's very easy to do that in Python. We just import that function from the scikit-learn matrix pairwise package. We generate embeddings for the query, and just go over everything and compute a cosine similarity. The result you see on this data frame, and cat is a cat. The similarity is 1.0. That's it. Cat and kočka is almost the same thing. It's 98% similarity, and then you have a really sharp drop, and you can see how the similarity goes down. And strangely, this might seem, this is the basis of every semantic search, every recommendation system you are using or somebody's forcing you to use. every sentiment analysis, etc. It's much more complicated in the implementation usually, and we will see a more complicated implementation, but that's about it. It's just math. And I promised no equations, mostly because I don't understand them, right? But I was curious, cosine similarity. Okay, you hear it all the time, and the worst thing, people do is they tell you, hey, it's just a vector. And you're okay, maybe, it's completely confusing. So again, in Python, we can kind of get some, at least little understanding what's going on. We will have 3 vectors, and for our purposes, vector is the same thing as that dot. It's not just a point on the plane, it's something which has a direction and a magnitude. The length is basically the magnitude, and the direction is the angle. We will create these vectors, which look like that. They are not esoteric, again. It's a matrix, nothing complicated. And we will compute, again, the cosine similarity for this matrix. That's the first panel out there. And we will kind of do the reverse operation for the cosine similarity using the rcosine function from NumPy package. And don't worry about the math, But when we then plot it with the quiver function, we immediately see what's going on. So all these vectors start from 0, and they have some kind of direction, same magnitude. A and B are almost the same thing. It's just 1 degree difference. And A and C, it's almost 30 degrees of difference. So these are really, really different. And this, my friends, is all. That's it. Every other system which uses vectors for search, for similarity, is based on this intuition. It's more complicated usually in the implementation, as I'm saying, but this is the thing behind it. One biggest insight I got from my research was this: if you have numbers, you can do math with them. And now it sounds like a dead joke, right? But it's a really profound intuition, because we are not using words themselves as the lexical items or their graphemes or phonemes. We're using their numerical representation, these embeddings. And when we can do something else with them. Do you know what happened? Or so we're back? Yeah, we're back. Really sorry. That's what you get when you're stressing out for a week that your talk is too long, and you iterate for like 4 times to compress it, and you remove slides. When you download the notebook, you will see like 10 slides or 15 slides I had to completely remove. So yeah, 10 minutes. So yeah. Let's hope we will make this journey. And you can always ask me questions afterwards. So I'll really try to, fast forward it, and then we can talk, for the rest of the day. So I've mentioned these numbers, and you can do math with numbers. Can you do math with words? Can you do something like king minus man plus woman is what? Possibly you've heard this formula. It's actually from Tomáš Mikulov, originally at the Brno Technical University, and then in Google and Facebook as a words to whack famous formula. Can we try it here in Python, and kind of, abusing the model a little bit, because this model is not really, tailored to words. So we will get the embeddings for king, subtract the embeddings for man, and subtract the embeddings for woman. And mind you, not the words that wouldn't have any meaningful sense, right? These numbers. What we will get is a result with a long list of numbers. Again, the same thing. There's nothing really crazy there. What if we could, again using the cosine similarity function we've seen previously, compute the similarity between each of these words and the result? So the result from that array is queen, almost a perfect match, 80% match. And then it kind of drops to king and woman, saxophone. Why is man, lower than saxophone? I mean, a king is kind of, that's man, right? If you think about it, it makes complete sense because we are really subtracting the meaning of this concept, man, from the king. We are telling the code, completely remove all meaning related to man. And there are many, things you can do with this. J. Alamar has a really nice illustration of this concept. I really encourage you to have a look at it. But let's have a look at a use case. Hopefully we can manage. Please yell at me, if I'm not too fast. So semantic search is actually a pretty good use case for text embeddings. And the traditional lexical search uses a lot of mathematics as well. The TF-IDF, term frequency, inverse document frequency formula. It's math. It works with vectors as well. But it works with the vocabulary terms. Still, it cannot do anything else than compare words. And yes, you can do lemmatization, and you can kind of transform it, and you can have synonyms, but it's just words. Semantic search works with meaning, not these terms. And the basic algorithm for implementing that is something called nearest neighbors. And when you now remember the plots, the scatter plots we did, that's what it is about. It's basically finding the nearest points in space. Not two-dimensional, the dimension is like thousands, but the math is still the same. So the most easy implementation we can have is, again, from the scikit-learn package. We can load the nearest neighbor class and a min-max scaler. We can feed all these embeddings from the data frame into it, normalize the distances, so they are between 0 and 1, and display them. And we use food, the word food, as a query. Now, pizza has a perfect distance to that concept. I mean, some nutritional evangelists wouldn't agree, maybe, but for the rest of the people, that makes complete sense. Pizza is a perfect match for the meaning of food. Then we get coffee, kind of makes sense. Dog and cat, and asymptomatic is completely, unrelated. It's completely unsimilar. Makes sense. It's a weird word. That's why I use that for demonstration purposes. But we can also use something more advanced and something which has been used in production, actually. And that's the Annoy library from Spotify, which for a long time has been used for music recommendations and still is in some parts. I will rush through the code because you can always download it from the Jupyter Notebook. We will extract the post titles from XML into Pandas data frame, compute embeddings, build the index, and search it. So let's go. This is a demonstration how pandas are useful. You just call read XML, and that's it. We drop everything apart from title and rename it to text. And this is how it looks like. Everything in this dataset is about coffee, obviously. We will compute the text embeddings, as we did before. We will build the index, passing the dimension, adding every embedding from our set, and we will save that index on disk. This part is not necessary for this demonstration, but this part is crucial for the production use of Annoy. Because think about it. Once you have built this file, you can put it something on like S3, download it to any server out there, and you have massively distributed semantic search or recommendation system. So we will define a very small function for searching and perform the search. You can see it's pretty fast. It's not much data, but it's still pretty fast. And if we search the Coffee Stack Exchange website for how much coffee can you drink in one day, notice how the results are really very relevant. The relevance is really high. But OK, what can you do with semantic search is that you can rephrase the query. And you can use words which are actually not contained in the corpus. Maximum coffee consumption for a human perfectly matches the daily intake or whatever. But these words are not in the titles, actually. And you can see that the results are still there, still very relevant. And it shows when you search for that same phrase on the Coffee Stack Exchange website, it gives you just 2 results. And notice the titles. These are not even that relevant. And what we can do even, because if you haven't noticed, we've used the multilingual model, we can use a different language as a query. We can say, kolik kafe můžu denně vypít, how much coffee can I drink daily, and we still get results in English. It doesn't make any sense to search for this on the Coffee Stack Exchange website. Obviously, it has no notion of a Czech meaning. There are vector databases these days who are much more powerful than the Python package, obviously. Postgre with PG Vector is pretty powerful. Elasticsearch has been doing a lot about semantic search lately. I wrote a blog post on this link, but there are many others, smaller ones, Pinecones, VV8, Vespa. And we're going to finally, because okay, text, that's cool, but there are many other things in the human world. And they say that picture is worth 1,000 words. So can we use something like that for pictures? We can. And for this demonstration, we will use a part of this Lion dataset. It's 2 billion image caption pairs. It's completely massive. It's 6 terabytes when you download it. And there is a perfect blog post, really nice, encourage you to read it, which downloads it all and does a semantic search engine. And it casually says, ensure you have at least 20 terabytes of disk space. I mean, that's kind of crazy, okay? So we will download just one single file from the dataset, metadata and 2 embedding files. When we peek inside the dataset, it's basically the caption, the URL for the image. It doesn't have the binary files. It has just URLs. And for some images, it has this EXIF metadata and others. When we display it, it looks like this. It's really heterogeneous. This dataset is perfect because it's not just photos, it's not just pictures. You can see there is a scan document and a drawing and a photographic portrait and a poster and whatnot. So what we can do is we can use a model from sentence transformers again, load the image embeddings from disk, and display the results for a query. So if we query the dataset with something like cat, dog, pizza, coffee, asymptomatic, which I couldn't resist to query it, it's a crazy bag of words. We do cross-modality search, so-called, because we search image embeddings with text embeddings. And this is the outcome. And the outcome is pretty good, I would say, because you have a coffee mug with a dog, and a dog with a pizza, and cats and dogs, obviously, and something called catpuccino, I never heard that, So I discovered catpuccino in this data set. And what we can do in closing is to search the dataset with a picture. So let's load this picture of a forest from Unsplash, using the Python image library, compute that embeddings, and display the results. And these are the results. I would say the visual similarity is striking. And in closing, this is not all. People invent new and new use cases for embeddings. Can we have embeddings for smell? Actually, a while ago, there's a project and a company called Osmo AI, and you can read it on these links. They trained a model on more than 5,000 molecules, matching them to human labels, like is it fruity, is it floral, etc. And they can match human evaluators using text embeddings. So thank you so much. I hope we finished on time. Thank you.
It's all numbers, right? This was a really big loudness value. What is your point of view for the recent controversial question in the field? Do large language models really understand meaning, or is it just statistics?
It's a great question, whoever asked it, because I would say it depends on how you define understanding the meaning. I would say they 100% understand the meaning in a sense. I read this text and I know what it's all about. But you might have a different definition for the word understanding, and then obviously they don't.
Have you ever fine-tuned a sentence transformer? If yes, what are the challenges that you face, and how much data did you use to retrain the model?
The beginning of the question was?
Have you ever fine-tuned a sentence transformer?
Found what? I'm really sorry.
Fine-tuned.
Fine-tuned? No, not really. I just used the pre-trained model. I mean, we had a use case where we fed it like millions of documents, and it worked very well. With a paraphrase multilingual model, by the way. It searches, in English, Czech, Greek, Russian, Polish, whatever.
Here's an interesting one. Why were the cat and dog positions rotated when you added pizza and coffee? Why were they different on the plot?
Well, yeah, I'm not sure. Sorry, that's how the PCA algorithm works.
If you have questions from the audience, please raise your hand. I'll come to you.
First of all, thank you very much for the speech. It was absolutely wonderful.
You're welcome.
And maybe there was one part that I didn't quite get, which had to do with the embeddings and the dimension. So forgive my ignorance in the topic of machine learning, but could you just elaborate a bit more on that? So what does it mean, the embeddings with dimensions? And those long list of numbers, how does the algorithm come up with those numbers?
Yeah, right. So I would say if you look at it from the, I'm going to use it in some way perspective, the longer the bigger the dimension, the better the model can understand, small aspects, like really, some nuances, basically, let's say. The small models, they don't understand that much. And how it comes with the dimension, that's the training part, and that's really much more complicated than this. I would say I've tried it, and it's much more complicated.
Thanks. Can we decode a vector in concept space to find a word as close as possible to that vector? And can we find gaps where we don't have words for a concept?
Wow, that's a really dense question. I don't know if you're trolling me or not. I would rather answer that in private, I'm afraid.
All right, so the space to find Karel and ask questions in private is right there.